Hi, welcome to the course Quantitative Methods in Chemistry. I am Bharatwaj Satyamurthy. As we had explained in the introductory video, will be handled by Dr. Ashish Srivastava and myself. For the first week of lectures, I will be handling the topics as we had decided before in this course. The topics that will be covered for this week would be chemical stoichiometry and the parameters to define concentration of chemicals. So basically this is important for chemists to understand how to quantify different chemicals as we will be dealing with different reactions as we go forward. And the different types of concentrations will be defined here, namely the normality, molarity, molality, mole fractions, ppm, that is parts per million, and also understanding analytical concentrations and equilibrium concentration in terms of thermodynamic parameters and also p-value for a given concentration. Let's go a little bit in detail about the learning objective here. Here we will be defining various parameters that we would like to understand and relate them across each other, meaning that how is molarity related to normality, molality and so on and so forth, and how the fundamental concepts of concentration of chemicals would help us deal with defining different chemicals that we might end up using in any of the reactions going forward. And of course, the last part would be associating them with thermodynamic parameters, which we will see at the end of this week of lectures. To start with, the first point that one should always remember that quantitation of chemical concentration came back from Avogadro's time. And in 1820, Avogadro hypothesized that equal volumes of different gases contain the same number of particles at a constant temperature and pressure. There are two words that I have put up here, which is ideal. At that point, definition of ideal gas was still being under works. It was not completely done. Basically, it is assumed that ideal gases of equal volume have the same number of particles at a given pressure and temperature. And remember, here we define particles is largely because sometimes there are gases which are just single atoms, and sometimes gases could also be made of molecules. So that's why the particle is a general term given for atoms, molecules. So this was an important step, largely because one would understand that defining a given number of molecules for a chemical started with such a definition. Here, as he mentioned, 1 mole of a gas occupies 22.41 liters at 1 atmosphere pressure and at 0 degrees Celsius. So this was a definition that was given by Avogadro towards quantifying the number of particles present across different chemicals, in this case the gases. This was followed by Joseph Loschmidt, who employed kinetic theory of gases. Of course, here is where the definition of ideal gases was completely put forth, saying that there are no attractive or repulsive forces between the molecules, and the molecules occupy very much smaller volume than the container itself. Using this theory, he was able to determine how many particles are present in a 1 centimeter cube at standard conditions. Once again, standard conditions here defined as 1 atmosphere pressure and 0 degrees Celsius. Moving forward with these two definitions, it was indeed in 1909 that Jean-Baptiste Perrin estimated the Avogadro number using Brownian motion. One should understand that getting an idea of Avogadro number requires measuring mass of a molecule and at the same time in its macroscopic fashion. That is, you need to measure mass of a molecule and mass of a given number of particles so that you can determine mass per particle and so on and so forth. The Avogadro's number was precisely determined by, in fact, the Millikan's oil drop experiment. Until that time, it was known that the Faraday constant is given by something approximately equal to 96500 coulomb per mole of electrons. Once Millikan was able to determine precisely the charge of an electron by his experiment, that is 1.6 10 to the power minus 19 joule, that is equivalent to 1 eV, then a simple division of the Faraday's constant with that of the electronic charge gives us what is the value of the Avogadro's number. As we see here, and most commonly people have known this, this is approximately equal to 6.022 into 10 to the power 23 particles per mole. In case that you are dealing with atoms, it will be atoms per mole in case you are dealing with molecules, number of molecules per mole, and so on and so forth. So now let's get into the idea of what is mole and molecular weight. 1 mole of a substance has a mass that is equal to its molecular weight. As you see here, molecular weight is defined in atomic mass units or gram per mole or Daltons. And to the right hand side here, what you see is the periodic table given by IUPAC, which attributes different features such as the molecular mass of a given atom and its isotope. Let's take for an example, what is the molecular mass of carbon dioxide? And as you see here in the periodic table, it's given by the mass number down here. The mass number for carbon is given as 12 AMU approximately, and then that of oxygen is given as 16 AMU. This indicates the total number of electrons that is present, while the mass number is indicated by the mass of the protons and neutrons that are present in the nucleus. So as we go forward, let's ask ourselves, what is the molecular weight of carbon dioxide? This is given by 1 atom of carbon and then 2 atoms of oxygen. This results in a 44 gram per mole of carbon dioxide. So basically 1 mole of carbon dioxide weighs 44 grams. So as we move forward, okay, is this the right molecular weight of carbon dioxide? Because carbon tends to have different isotopes. As shown here, carbon could be present as C12, C13 or C14. At the same time, carbon dioxide, the oxygen in carbon dioxide could be present as O16, O17 or O18. And as the numbers indicate below, the carbon 12 is the most stable and the abundant nuclei, with carbon 13 being present at 1% abundance, while C14 is traces. So for all practical purposes, we will not be employing this for our calculation going forward. On the other hand, oxygen 16 is the most abundant, followed by O18, then followed by O17. The previous slide showed you the calculation of molecular weight, assuming that the isotope of carbon is C12 and that of oxygen is O16. Now let's take a look at the fact, what if we consider the population weighting. So basically what is going to end up happening is that for C12 plus O16, you're going to have the calculation that is driven by the fact that 0.9889 times 0.9976 times 12 plus 16 times 2. This is where you are getting CO2, where 12 and 16 are factored in. On the other hand, if you are going to have 12C plus 17O, you are going to get something like 0.9889 times 0.04 times 12 plus 17 times 2. If you do the math, you are going to get something close to 44.01 grams per mole. We tend to assume that C12 and O16 constitute towards molecular weight of carbon dioxide, and therefore we tend to say 44 grams per mole is the molecular weight of carbon dioxide. As you have seen in this detailed discussion, that isotopes do end up mattering. So depending upon the concentration of these isotopes, one has to be careful defining what is the molecular weight for a given chemical. So let's quickly define what is chemical stoichiometry. Stoichiometry is the quantitative definition or description of proportions by moles. Once again, we just defined moles in a chemical reaction. Let me repeat, stoichiometry is the quantitative description of the proportion by moles of the substances in a chemical reaction. Let's take for an instance combustion of methane. Methane is CH4 and combustion happens in the presence of oxygen that results in the formation of carbon dioxide and water. Of course, here we are assuming it's complete combustion. First thing that we have to end up doing is that we understand you have 2 atoms of oxygen here while you have 3 atoms of oxygen here. So first step that would be involved in getting a chemical reaction to understand its stoichiometry would be balancing it. So the first act of balancing would be one where, let's take a look at the number of carbon atoms. You have one carbon atom to the left side and one to the right side. That means it's already balanced. You have 4 atoms of hydrogen, well you have 2 atoms of hydrogen on the right hand side. So it might make sense to add a 2 there. And then when you pay close attention, you see that you have 2 atoms of oxygen on the left side while you have 4 on the right side. So therefore it makes sense to have CH4 plus 2O2 giving CO2 plus 2H2O. So this process is called balancing of chemical reaction that helps us understand stoichiometry. Once that we have balanced this equation with the appropriate number on either side of the reaction, the next step would be understanding what is the stoichiometry that is involved. CH4, the molecular weight of CH4 is going to be 12 plus 4, that's going to be 16 grams. And oxygen is 16 times 2 and you have 2 of those. So basically you are going to have 16 times 2 times 2, that's going to be 64 grams. And carbon dioxide, as we have just discussed a few moments back, is 44 grams. And water is going to be 2 plus 16 times 2, that's going to make it 18 times 2 on the right hand side. Basically this is going to be 36 grams. Understand that you have 1 mole of methane reacting with 2 moles of oxygen to give 1 mole of carbon dioxide and 2 moles of water. As you see here, the equivalence or the stoichiometry that goes is that if 16 grams of methane reacts with 64 grams of oxygen, it will result in the formation of 44 grams of carbon dioxide and 36 grams of water. So basically this is what we mean by stoichiometry, and the important thing one has to understand, when the reagents are added in stoichiometric amounts, then upon completion of the reaction, neither will the reagents be present in excess nor be required any further. This just indicates the fact that all of the reagents will be used and there will be none that will be required any further because all the other reagents would have been completed. Let's try to take an example to understand this a little further. The example being sodium carbonate reacts with silver nitrate. So let's start writing, and there are at least a few more things that should be added. In addition to the grams that is given for the stoichiometry, one also gives the standard states at which the different reactants and the products are present. In this case, methane will be present as a gas, oxygen will be present as a gas, carbon dioxide will also be present as a gas, water is a liquid or gas depending upon the temperature that we are dealing with here in this combustion process. So if the temperature is high enough, it's not going to condense and you're going to see water vapor. So in this example, we are going to be looking at sodium carbonate plus silver nitrate resulting in the formation of silver carbonate plus sodium nitrate. As always, the first step is going to be balancing this reaction. As we see on the left hand side, we see 2 atoms of sodium and only 1 on the right side. So let us see whether if we write 2, whether it helps or not. Just for the sake of clarity, let me try to change the color of the pen I will be using just to indicate the balancing. So let's add a 2 here. That's 2 atoms of sodium on the right and we already had 2 on the left. Carbon is present as 1 atom on both the sides. Oxygen on the other hand, left hand side has 6 while right hand side now has 9. Let's go on and see that silver, there are 2 atoms on the right and 1 on the left. So it might make sense to add a 2 here. This takes care of the nitrogen and oxygen being carefully balanced. So basically this is the balanced reaction and all of these are present under aqueous conditions. Okay, now that we have balanced the reaction, let's try to ask ourselves what is the stoichiometry, meaning how many grams per mole are required for each one of this. Sodium is 23 while carbon is 12 and oxygen is 16. So basically you are going to have 46 plus 12 plus 48, that takes it to 106. So that will be 106 grams per mole. Now that we have obtained the molecular weight of all of these constituents of this reaction, let's try to understand how many of what is required. So, 106 grams of sodium carbonate will react with 340 grams of silver nitrate to give 276 grams of silver carbonate and then 170 grams of sodium nitrate. So, basically this is the stoichiometry that we are looking forward for such a reaction. Going forward, let us take a question here. How many grams of sodium carbonate is required to completely convert 8 grams of silver nitrate to silver carbonate and sodium nitrate? So, let us quickly rewrite the whole equation again. I am going to go back to red. So, the question here is that if you are having 8 grams of silver nitrate, how much of sodium carbonate is required for completely using all the silver nitrate that is present. So, for instance, all that we have to do here is that for 106 grams, 340 grams is required. So, for 8 grams, how much is required? So, it is going to be equal to 8 by 340 times 106. That is going to be equal to 2.49 grams of sodium carbonate. And now that we have understood 2.43 grams of sodium, 2.49 grams of sodium carbonate is required, let us also determine how much of Ag2CO3, that is silver carbonate, will be formed. Using the same formula, you are going to have 8 by 340 times 276, which is going to be equal to 6.49 grams, and how much of NaNO3? It is going to be equal to 8 by 340 times 170, which is going to be equal to, this is easy, it will be 4 grams. So, basically if you have 8 grams of silver nitrate that is present, you need to add about 2.49 grams of sodium carbonate, which will yield you 6.49 grams of silver carbonate and then 4 grams of sodium nitrate. So, this I hope helps you understand how does stoichiometry go. Depending upon the concentration of one reagent, the other is carefully added such that no more of the reagents are required to form the products and none exists at the end of it. So, let us quickly understand the concept of limiting reagent. We just understood that 16 grams of methane reacts with 64 grams of oxygen to give 44 grams of carbon dioxide and 36 grams of water. And one has to remember that what happens if you just had 8 grams of methane while you had still 64 grams of oxygen. When this happens, what you are able to realize is that 8 grams of methane is only going to about use 32 grams of oxygen. This results in an excess of 32 grams of oxygen. So, basically this is a reaction where the methane appears to be a limiting reagent. What do we mean by that? We mean that since the concentration of methane is less, it limits the reaction to go any further, although oxygen is present in more excess. So, this is an example where one is able to understand these are not given in stoichiometric ratios, resulting in one reagent being in excess. So, going back a little bit to molecular weight, let us recap a small portion of this. You understand that atoms weight is going to be given based on its isotope. Molecules such as water, which has 18 grams per mole, is given by the sum of such atomic weights. And you could also have chemicals. We just saw an example where sodium carbonate, which is going to be 46 plus 12 plus 48, making it 106 grams per mole, is assuming there is no water of hydration present. You could be purchasing salts that has water of hydration, meaning that these waters cannot be removed from the final solid product that has been obtained. And an example as taken here, sodium carbonate that has 10 water of hydration. This is sodium carbonate decahydrate is going to have 106 grams plus 18 grams times 10, which is going to be 180. So this molecular weight of the same is going to be 286 grams per mole. On the other hand, if you are going to larger molecules, as you see here, this is a molecule of sucrose. Sucrose is made by the combination of glucose and fructose, and as you would all know, glucose and fructose are isomers of each other, meaning that they have the same molecular weight. They are about 180 grams per mole, and sucrose is formed by the condensation of glucose and fructose with elimination of one water molecule. So basically that's going to be 360 minus 18, which results in 342 grams per mole. So what one is able to understand here is that molecular weights can be determined from the constituent atoms or molecules that help forming them. Going to macromolecules, as in the case of proteins as shown here, this is a famous protein called myoglobin. It has a lot of atoms as seen here. It has 783 carbon atoms, 1240 hydrogen atoms, 216 nitrogen atoms, and 216 oxygen atoms, and 2 sulfur atoms. Of course, you can take all day to sit and calculate its molecular weight. I had come prepared here. This is about 17,199 grams per mole. Generally in the field of proteins, this is going to be called as Dalton. So this is also referred to as 17.2 kilodalton, which indicates the molecular weight of myoglobin. Now let's go to the first concentration unit that we will most commonly use in this field of chemistry. So that is called molarity. Molarity is defined as the number of moles present in a given volume of solution. So basically molarity M is given by number of moles, which is unitless, divided by the volume of solution in liters. And as we just saw, the number of moles is going to be given, let's say, the weight of the solute of the chemical in grams, dividing that by the molecular weight, which we just understood how to calculate, times the volume of solution in liters. So this will end up as a unit such as moles per liter. So this is the definition of molecular weight. Let's go back to our sodium carbonate. In this case, let's not assume it's a decahydrate to start with. So the question here is, what is the molarity of 10 grams of sodium carbonate in half a liter of solution? In this case, we are assuming addition of 10 grams to half a liter of water results in half a liter of solution, which need not be the case all the time, but let's assume the same to start with. So we know that the molecular weight of sodium carbonate is 106 grams per mole, and we have 10 grams of it. So the molarity is now going to be given by 10 grams divided by 106 grams per mole. Just for the sake of easiness, let's assume we have 10.6 grams of sodium carbonate. That makes our math easier, times volume of solution in liters, and you have 500 ml of solution, let's say. So that is going to be 0.5. So basically this is going to be something like, this is 10 and this is 2, so you're going to have 1/5, that is going to be. So 10 grams of sodium carbonate in water, in half a liter of water, constitutes 0.2 molar. We have just determined the molarity of sodium carbonate in half a liter of water when you have 10.6 grams of sodium carbonate. Let's try to twist the question over and ask the same thing in a slightly different manner. We are asking how much amount of myoglobin is present in 100 microliters of solution that is having 5 millimolar concentration of myoglobin. Let's go back to our definition. Molecular weight is given by weight by molecular weight times volume of solution in liters. Here volume of the solution is 100 microliters. So we are asking what is the weight in grams. What is the molecular weight? We just learnt it is 17.2 into 10 to the power of 3 grams per mole times volume of solution in liters. It's 100 microliters. So therefore, the way to determine how much weight is present, and remember the left hand side is 5 millimolar. So therefore, the weight in grams of myoglobin is going to be equal to 5 into 10 power minus 3 times 17.2 into 10 to the power of 3 multiplied by 10 power minus 4. So this is going to finally result in 17.2 times 5 . So basically it's going to be 8.6 into 10 to the power of minus 3 grams, which is 8.6 milligrams. So basically if you dissolve 8.6 milligrams of myoglobin in 100 microliters solution, you're going to finally end up with a 5 millimolar concentration of myoglobin. With this, let us stop the first lecture. We will continue the forthcoming lectures by trying to define other units of concentration such as normality, molarity, weight percent and so on and so forth, and try to go forward in understanding how all these different units of concentration help us understand or define concentration of chemicals that will be used in different reactions. Thank you.